so much. I kindly thank Professor Witlin for his invitation to present some lecture on the research studies done by me and coworkers. And I feel a little bit embarrassed because I quite frequently present results for Institute of Physics, but again, I hope that today I could give you also some information which might be inspiring because of, I would, to my taste, of pretty general interest. So the talk is going to be devoted to Josephson effect, and I divided it in two parts. The first one is of a very general introductory character. So you can think of it as a preliminary part, and those of you who are familiar with Josephson effect, you please forgive me for repeating some obvious information on it. And the second part is related to my own activity, not very recent, but I think that it's still quite a hot topic. So it would be related to topological superconductivity. To start with, I would like to show this setup consisting of, well, this is tunneling system consisting of the left and right-hand side superconducting reservoirs. They represent macroscopic systems where we have some effective electron pairing, formation of Cooper pairs, and we assume these Cooper pairs to be Bose-Einstein condensed in a coherent phase. As you know, Cooper pairs can be characterized by the wave function, and wave function by itself is a complex quantity. So we can think about the absolute value and also the phase. And this phase on the left and the right-hand side, if they are different, this might lead to diffusion of Cooper pairs through some thin interface, and such interface can be either insulating, semiconducting, metallic. I will give you a few examples. So as far as theoretical prediction of this pretty spectacular effect is concerned, it has been predicted by Brian David Josephson in 1962 when he was a PhD student at Cambridge in England, just 22 years old, a fellow. So his paper published in first issue of Physics Letters was based on a simple treatment of the tunneling processes in a perturbative way. So you can just pick up a chapter of the book by Mahan and learn everything and rederive it by yourself. So actually, this topic, I suppose, was suggested by Isitor at that time in his institute. I mean, Philip W. Anderson. Some noise in the background. I hope it's not my fault. Okay, it's now okay. So there are two basic predictions which we assign to Josephson. Already without any voltage between left and right-hand side electrodes, there is possible flow of Cooper pairs, and this is a phenomenon of so-called direct current Josephson effect. However, we can also think about some biased setup, and under such circumstances, charge flow from left to right and back has an oscillating character. So this is alternating current Josephson effect, and the frequency is proportional to the bias voltage. From the present day perspective, I would say that this prediction of DC Josephson effect is so trivial, it's quite surprising. So let me give you the only, let me present just the only slide with formulas to show how in 3 steps we can convince ourselves that phase difference is going to induce superflow of Coupe pairs. In a quantum mechanics, when we talk about a system described by wave function psi depending on position and time, we can also think about, the absolute value of the wave function tells us about the probability of finding particle in a system. However, we can also consider probability current, flow of particles, if you wish. And formal expression for such current probability operator is given by this combination of psi dagger and gradient of psi minus its complex conjugate. If you apply this expression to the wave function of Coupe pairs of some superconducting reservoir, and you keep in mind that that the wave function is a complex quantity, so we can represent it in terms of absolute value, magnitude, which actually is nothing else but square root of concentration of Coupe pairs in this case, and phase. I denoted it by phi in red color. Then, after substituting this wave function to the definition of current, in this case, I'm denoting it with J subscript to refer to the Josephson current, you can convince yourself that real parts of the first and second term cancel each other, and you are left with solely imaginary parts. So when you multiply with this coefficient here, and also we simply obtain the very well-known expression for current density, which is equal to charge times concentration times velocity. Of course, in our case, charge is here a double elementary charge. And please notice that velocity in this expression for the current is strictly given by a gradient of the phase. In other words, if you have non-homogeneous superconductor and if you have a spatial variation of phase of Coupe pairs, it is automatically inducing superflow of Coupe pairs. So in particular, if you have left-hand side and the right-hand side superconducting regions interconnected by some insulating barrier, then the difference between phases is the driving mechanism of this superflow. So it's pretty obvious, but I must admit that probably prediction in 1962 was very astonishing, and to many physicists probably also quite, people might be suspicious. But it's this prediction was confirmed experimentally by Phil Anderson, who is after all prominent theoretician. That indeed in some superconducting tin, in a superconducting, well, I'm not sure whether the superconductor was lead or tin, but in this setup they used with a thin oxide barrier, they observed some small current even without any voltage. Of course, there is also increase of current once you exceed the gap of superconductor. So this is well-known phenomenon. So please notice that experimental evidence for the Josephson effect was just with 1 year delay with respect to the prediction. And 10 years after discovery, experimental discovery, Brian Josephson was awarded Nobel Prize together with Sasaki and Giaver, who were awarded half of the Nobel Prize for tunneling experiments. I guess superconductivity in 1973 was extremely popular because it was just 1 year after Bardeen Cooper Schrieffer Nobel Prize. So 2 Nobel Prizes in a row were awarded for the superconductivity. For our present understanding, what's important is this characteristic current versus voltage plot. So we can transmit charge flow through the junction without producing any voltage. But of course, there is some critical magnitude of this current. Once you exceed it, then the system automatically switches to the resistive behavior. Of course, this magnitude of the critical current is sensitive to many ingredients, in particular to temperature. With increase of temperature, it is becoming smaller and smaller. Of course, this could be problematic, but of course, some people can even are clever enough to make practical use of this property. A colleague of yours from Institute of Physics of the Polish Academy of Sciences, Maciej Zgierski, invented the device which is able to measure temperature with nanosecond precision. So this is ultra fast nanoscale thermometry, and plenty of other closely related applications. Let me come back to the initial setup. So when we consider 2 superconductors linked by some narrow region, then, of course, upon imposing phase difference between wave functions on the left and right-hand sides, we expect superflow or flow of Cooper pairs. And in a natural way, the larger the phase difference, the larger the current. But of course, it has periodic character. So this sign dependence on phase difference between the left and right-hand side is quite natural. I would like to give you a few examples from the recent studies, theoretical and experimental, where this periodicity is violated, and such departure from the periodicity is related with some physical effects. So imagine that you, for example, have left right-hand side superconductor, instead which interconnected not via some link, some insulating barrier, but by some small object like a carbon nanotube. And this nanoscopic object is effectively representing a whole bunch of discrete energy levels. And if it happens that one of them is inside of the gap of left and the right-hand side superconductor, then such energy gap can be used for transmitting left or right Cooper pairs. It has been predicted, or maybe not predicted, but it has been observed and in the same paper also interpreted by my colleague Tomasz Nowotny, with whom I have tight collaboration, that depending on the energy level of this quantum dot, which can be varied by side-attached gate potential, the current can suddenly not only change the magnitude, but also can be reversed, can change its direction. So if you talk in terms of left, right-hand motion, then this is like pi rotation, and people call this phenomenon zero pi transition. I guess one of my colleagues, Piotr Przystupski, is familiar with this phenomenon. I can give you microscopic reasoning behind this phenomenon. Actually, a few years ago, 5 years ago already, jointly with Tomasz Nowotny, we inspected such a circuit with left, right side electrodes, superconducting electrodes, some impurity, which is represented by a single level discrete energy level. And additionally, this energy level can be either its energy can be varied. So as a function of phase difference between left and right, we predicted that there is a sudden drop of magnitude and reversal of the Josephson current. So once again, this sinusoidal natural prediction of the DC Josephson current is not always true. I mean, if you have correlated impurities sandwiched between the external reservoirs, some phase transitions which take place on this nanoscopic object can completely invert direction of the Josephson flow. Maybe this is not very much useful for practical purposes. So something which is of much greater interest for the scientific and not only for scientific community is a perspective to build quantum bits out of bound states on impurities. In particular, if you consider Josephson junction, there are two possible means to realize quantum bits. One of them is basically a setup reminiscent of SQUID, of superconducting quantum interferometer device, where you have two junctions, this one in the bottom, in the top, and forming a closed circuit, which is also in presence of magnetic field, of course, can give rise to interference between upper and lower branch of this transport channels. So depending on the current, you can realize different configurations, which can, in this larger configuration, be used to construct so-called transmon. Other option is by using simple Josephson junction, where you attach gate voltage, and by lifting or lowering the quantum states, quantum energy levels, in this electrostatic mean, you can control also information stored on this quantum bit. So this is known as gatemon. And of course, there is intensive activity in this direction. I would like to show you maybe the first example of this electrically controlled quantum bit. So the setup is practically Josephson junction, left, right side superconductor, and some nanoscopic objects. It can be, in this case, it was, if I remember, semiconducting nanowire with discrete energy levels, and the gate potential to control value of such energy levels. So yeah, if I remember, this group from Nordita from Copenhagen used indium arsenide nanowire, and superconducting electrodes were made of aluminum. So in electrostatic way, they were able to realize various, they were able to realize quantum bits, and experimentally estimated that relaxation time and the dephasing was on the level of microseconds, which was fairly satisfactory. There are more recent realizations of quantum bits. I don't want maybe to discuss such details. Something which is extremely intriguing is also, this is third example, possible realization of selective Josephson superflow. Selective in a sense that Josephson current is able to flow only from one side, from say left to right, whereas in the opposite direction, I don't know where this voice comes out. So this is like a diode, like semiconducting diode with a PN type components. In this case, of course, such Josephson diode can be realized using additional support of magnetic field, but less than 1 year ago, in April 2022, there was a paper where van der Waals heterostructure consisting of this conventional superconductor and diselenium niobium and then bromide niobium was able to realize this, let's say, Josephson type diode without need of any magnetic field. So the structure in principle looks like this, that you have some small region connecting niobium diselenide in the upper, in the bottom part. It's just a few atoms thick region, and it's possible to transmit Cooper person from one side to another, whereas if you force a charge to move from the bottom to upper part, then such current flow is resistive, is related with some finite resistance. So there is a lot of discussion on the mechanism behind this Josephson diode effect, and all theoretical papers in the introduction and also in the summary part admit that the true mechanism is not really well established yet. Definitely, what matters is this linking region between external superconducting parts. And this narrow region, this link inside, is made of such a material which is characterized by inversion symmetry breaking and also time reversal symmetry breaking. So in practice, you can see in this cartoon that if you, okay, now current is here on the horizontal axis. If you exceed current by some critical magnitude, then of course this junction switches from superconducting to resistive region. However, if you try to force the current into opposite direction, the critical value is for this negative direction, let's say, much smaller. So it's not truly resistive all the way from zero current to any other, but you quite clearly can notice left-right side asymmetry. So different critical values of the current. There is also some signature in AC Josephson effect, which manifests this diode, Josephson diode feature. Okay, since I already talked about 20 minutes, let me now switch to the main part of my presentation. I would like to tell you also that Josephson junctions, when properly constructed, can be also considered as a platform for realization of topological superconductivity. The topic is pretty fresh, pretty new. Some ideas in this direction were formulated about 5 years ago. There were two papers, one by a group from Harvard and another one from, if I remember, from Denmark. The suggestion, theoretical suggestion, the idea was like that. If we take two superconducting parts in a planar geometry, separated by a small region, which is semi one-dimensional. So it's much longer than it's compared to the width. Then in presence of strong spin-orbit interaction and with additional application of magnetic field, this little piece inside inserted between external superconductors can first of all absorb Cooper pairs, and due to this interplay of spin-orbit interaction and the Zeeman effect, this proximity-induced pairing in this linking region could evolve into the topological phase, hosting zero boundary modes, this gamma on the left and right side here. Why? I mean, the idea was appealing. So the reasoning behind was that normally we are either lucky or unlucky when trying to obtain topological phase in strictly one-dimensional systems like semiconducting nanowires or chains of magnetic islands. Here, if we, for instance, lithographically more or less form one-dimensional setup, then phase difference between left and right can be this knob, this mean to tune into the topological or to non-topological phase. So this was the main motivation. And once again, let me repeat that the concept, theoretical idea, again involved proximity-induced pairing, spin-orbit coupling of this metallic part, and some reasonably strong but not too strong magnetic field along the junction. If you consider regions of topological phase, then they form some shape of diamond type. So as a function of magnetic field, as a function also of phase difference, you can see a realization of topological phase. For instance, without any phase difference, this little part here would be conventional superconductor. If you move towards completely opposite phases, then practically for all magnetic fields, this metallic slab is going to be topological. Okay, so the idea was proposed in 2017, and pretty soon, almost as quick as with this prediction of Josephson effect and its empirical verification by Anderson and Rowell at IBM 1 year later. In this case, it took 2 years for two groups to reveal that indeed this topological phase with zero boundary modes close to the ends of such a heterostructure can be obtained, for instance, using indium arsenide. So this is two-dimensional electron gas, which is marked here by the gray color. And on top of it, this group from Copenhagen epitaxially deposited superconducting leads. And of course, they formed some loops. So by magnetic field, they controlled phase difference between left and right. So in this case, again, aluminum was used for the superconducting external leads. And the other method was done with tellurium mercury quantum well. This is the group of Lawrence Molenkamp in cooperation with with theoreticians from Harvard University. So, okay, maybe this cartoon is not quite easy to understand. So let me tell you that the region which is, so the superconducting part is here marked by gray color. Again, this is aluminum. And so you see here some magnetic field penetrating this superconducting left-right side regions. So this is the mechanism to control the phase difference. And this metallic part is marked here in this region. Actually, the real size was nearly square shape, because the length was 1 micrometer and the width was practically half of it. Well, these people were also able to approach some conducting, they found some quantum contact at the end of such a metallic region, and they did some measurements of the current through this tip to learn about the quasi-particle spectra. And their results are presented here for 3 magnetic fields in these D, E, and F panels. So practically, if we recall the phase diagrams, as a function of magnetic field, you could think about some phase difference, and this is buried here. So different colors correspond to different phase differences. They did measurements for 3 points indicated in this phase diagram. The left-hand side, this circle, corresponds to a situation without any magnetic field, when all this setup is is like a standard Josephson junction. There is leakage of Cooper pairs into this linking region, but it has no topological phase. So if you if you check the density of states, which is of course measured indirectly by tunneling conductance, you see a deep, which is well-known energy gap of superconductor. Actually, this is gap from 0 to 2 delta and from 0 to -2 delta. However, if you increase the magnetic field, and let me go to the right-hand side panel, which according to theoretical prediction would correspond to topological phase. Besides gapped structure, you can see that for some phases different than 0, like this pi half, pi, and 3 pi by 2, we see enhancement of the tunneling current, which can be assigned to the 0 energy quasi-particle residing in this metallic part. If I go back to this, oops, I'm sorry, to this cartoon before. So please notice they probed electronic spectrum at the end of this linking region between left and right side superconductor. I must admit that after 2 experimental studies, I hardly saw any other evidence. Probably it's not so easy to be really fully convinced that this 0 energy quasi-particle is Majorana type. And maybe it's not so easy also to incorporate Josephson junction into some more complex structures with possible realization of quantum gates and so on. I did some analysis of the true Majorana quasi-particles in such structure together with my former PhD student Stepan Głodzik. So in this region where you see, well, we have here a rectangular shape. So bottom and upper part is describes here the superconducting region, and this side from 10 to 15 is the metallic part with spin orbiting direction and magnetic field. So our theoretical prediction of something which is overlap of particle and hole, because as you know, Majorana quasi-particles are unique in a sense that creation and annihilation is the same. So particle and whole, so quasi-particle is both particle and it's antiparticle. So if you wish, if you find some information about such strange object, you could probably take a look on overlap between particle and whole of the Bogolyubov quasi-particles. So this quantity is in literature sometimes known as Majorana polarization, but the polarization is rather misleading. So it's particle-whole overlap. According to our theoretical results, indeed, Majorana quasi-particles should be at the ends of such a metallic region, but there should also have some oscillatory behavior. And of course, you can study the vertical and horizontal textures. In principle, this quantity is complex. It's like a wave function of Coupe pairs, but in this case, a particular pair referring to equal spin pairing. So, is there any way to experimentally probe such a quantity? We have shown that the possible way to analyze it is by using Andreev spectroscopy with spin polarization. The experiment for this particular system would look like this: that you approach the STM tip to a given site, let's say I, and you try to inject electron with a given, let's say, up spin. Normally, if electron picks up another companion of opposite spin and goes into the superconductor as a Coupe pair, you would expect hole with opposite spin to be reflected back. However, in topological superconductors, we are dealing with equal spin pairing, of course, not on the same side, because it is forbidden by Pauli principle. Pairs are formed between neighboring sides. So we inject, let's say, electron into J and extract a hole of the same polarization from the neighboring I side. This so-called Cesar spectroscopy actually was discussed by also distinguished theoreticians from MIT, and I was happy to find analytical proof that Majorana polarization, or strictly speaking, its absolute value, is identically is measurable by differential conductance of such spin polarized Andreev reflection. Yeah, let me now mention, okay, so this is some optimistic perspective that in quasi two-dimensional planar junctions, you can realize Majorana modes. This is different compared to these highly criticized ideas of having topological one-dimensional superconductors. But the problem is that, as you could see here, Majorana is kind of smeared over many sides. It has some spatial let's say extent, and if you think about using Majorana quasi-particles for quantum bits, you would rather prefer to have it well localized, located to either one side or very small region. So this smearing is not something to be avoided, something to be dealt with. And colleagues around Leo Kovenhoven, theoreticians, in Delft, in Netherlands, came with a proposal that instead of just rectangular shape, something like a D-shaped, zigzag-like shape is used between two superconducting leads. Then this scattering along the junction, along the interface, would be beneficial for localizing Majorana modes. And also there is also additional benefit, namely the gap separating such Majorana modes from all the rest, from all the other trivial states, when you deform this connecting part, it can be increased. So the gap initially in this straight configuration, which is something like 1/100th of the pairing gap of superconducting regions, in the deformed region can be changed to just can be increased 10 times. We did some Gedanken experiment, namely we thought about some other alternative methods to reduce the spatial extent of Majorana modes by using some external potentials, some external defects. For instance, by approaching a tip with a huge, with some voltage, locally energy of the electron can be either increased or decreased. So it can be driven away from the topological region. Normally, if you do such a trick, if you try to apply this idea to a wire, then you would kind of break the wire into two pieces. So you would double Majorana, a number of Majorana modes. However, here we are dealing with some quasi two-dimensional object, and we noticed that such defect has practically no influence on left-right side Majorana modes if it is approached to some central parts of such a metallic region. The situation is different if we move on with this defect, with this side-attached voltage, to one of the Majorana modes. In this case, the position of such a defect is indicated by arrow. So you clearly see that the size of Majorana mode, spatial size, is substantially reduced. So it kind of is tending to be more localized. That's a natural tendency of the boundary modes. Once you have some defects, they seem like the sources of confinement for such Majorana modes. If you go to a different extreme situation by increasing the size of this metallic part, then the Majorana would not only be smeared, but it would even be represented by a propagating edge mode, which is interesting from the fundamental, from the point of view of fundamental science, but probably not so useful for quantum computations or for quantum bits on Majorana modes. There were also other ideas, like, for instance, the one by Adi Stern, who predicted that by disordering this metallic part, disorder would reduce the extent of Majorana mode. But of course, there is also an opposite behavior once you exceed some critical value. Yeah, we were able to model this phenomenon. So in a uniform gas, so you see here profile of Majorana, left and right is identical. Then the left side with the random energies indeed confirmed the tendency towards localization. So there are some methods where you can do what you really think of. Let me now, in the very last few slides, 4 or maybe 5, show some new concepts. To my knowledge, there is no progress in this direction experimentally, but people try to suggest some closely related ideas. So one of them is this setup, which looks for us familiar, proposed by Daniel Loss and Jelena Klinowaya from Switzerland. They proposed to use germanium as this substrate, well, the metallic substrate. In this case, it's rather maybe semiconducting, and of course the charge carriers have whole character. What's appealing here is the natural this phenomenon that spin orbit interaction is pretty strong, and it's also quite exotic because it's cubic with respect to momentum rather than parabolic. So the appealing perspective is that since nowadays all electronic devices are made on silicon or germanium, then probably Josephson junctions with Majoranas based on such technology would be easy to incorporate into this SMOS technology. Something very surprising is the asymmetry for the behavior once you, I mean, the phase difference looks different when you vary phase between left and right, and it's asymmetric on the phase reversal. But I maybe will skip discussion on this effect. Something else which is quite interesting is a vertical geometry of the Josephson junction. Imagine that you have superconductor, well, planar shaped superconductor, and another one interconnected by a region which has its own magnetic texture. So there have been ideas already considered 5 years earlier that if this yellow part, this link between bottom and up superconducting regions, somehow contains spin helix magnetic textures. They call it persistent spin helix state. There is quite interesting literature on that. I'm sure that there are experts among you on this topic. Then very weak magnetic field is going to induce P-wave superconductivity, and with a great chance also for this P-wave superconductivity to evolve from trivial to topologically non-trivial phase. The very last idea, which I want to present to you, is my own concept, but mainly inspected numerically by Maciek Maśka, very well known to you. So in some analogy to one-dimensional systems, especially if you consider that on top of lead or aluminum, if you spread a chain of magnetic atoms, like iron atoms, they want to arrange themselves into spiral helical structure. We thought that perhaps if some magnetic sample, a very narrow magnetic sample, I mean, of a width safely smaller than the coherence lengths of Cooper pairs, is inserted between such superconducting regions. So this is, after all, Josephson junction setup with magnetic link in between. Then the proximity effect combined with classical magnets might give rise to some helical structure, and with some chance also to produce topological phase. We have done some calculations for finite size system consisting of 40 sites along the Josephson junction and 12 across, assuming that 4 sides corresponded to the left-hand side superconductor and 4 from 9 to 12 to the right-hand side. They could differ by phase, they can be the same phase. And this region in between, also consisting of 4 sides from 5 to 8. This is the region where we put classical magnetic moments. When self-consistently solving Bogoliubov-Dejean equations, we could determine profile of the S-wave superconductor, and you see it, of course, in the host left and right, and some S-wave pairing induced also close to the boundaries inside. But also we can see the pairing of the same spin between neighboring sides. And the P-wave pairing is solely represented in this linking region, where we have magnetic moments which self-organized themselves into such magnetic textures which give rise to P-wave pairing. Now, when you analyze the electronic spectrum as a function of this length and width, then for zero phase difference, we see no quasi-particles at zero energy. This is spectral function or density of states at zero energy or at Fermi level. With a differing phase, here you see pi by 5, pi by 0.4 pi, and we are going towards pi difference. The magnitude of zero energy modes seems to increase. Actually, we are not yet fully confident that the optimal conditions are at pi difference between left and right. This is still work in progress. Exactly the same today Maciek Maśka is presenting preliminary results during APS meeting in Las Vegas. So hopefully we can maybe pretty soon complete full set of the results. I gave also information about such our preliminary information to Lawrence Molenkamp 1 month ago during focused workshop at MACTOP, and he was pretty intrigued, and he is apparently also interested in maybe experimental realization of such a setup. So as a feedback from you, I would be happy to hear what sort of materials one could consider for practical realizations of such, let's say, magnetic type Josephson junction. Is a ferromagnet or something else? So since I'm not competent in this regard, I would maybe briefly summarize the second part of my lecture. So normally when we talk about magnetism and pairing, we know that magnetism is destructive. Magnetic field, critical magnetic field can completely destroy superconductivity in bulk materials, or we can have this mixed phase with vortices. So they are often considered as enemies. However, if you properly mix electron pairing, like for instance in also Josephson type geometries, where due to leakage of Coupe pairs to this linking region, you induce electron pairing. In addition to it, magnetism, either by originating from spin orbit locking plus Zeeman field, or by self-organization of classical moments, they can have cooperative character, and in particular, leading to topological states of matter with boundary modes. Of course, it's I could give you more precise information about the topological phase itself, because of course we know topological phase is characterized by invariance. So it's not just let's say minus plus z sub 2 type topological phase. This topological invariance can take here more numerous values. So there is some distinction between topological phase inside of it. But in principle, the message to take home is that magnetism and pairing, they give rise to emergent phenomena, in particular producing topological phase. If some of information presented by me is of any interest for you, then you can download PDF file of my talk from my web page. This is indicated here in the bottom, and Professor Wittlin promised also to make a link to this PDF. And the last slide is to acknowledge my coworkers, Maciek Masika, who did calculations for the very last part of this lecture, Szczepan Głodzik, who just came back from Ljubljana, from Rok Žitko, and is working on highly sophisticated issues with corresponding to quantum bits and so on. Axel Kobiałka is in Basel in Switzerland, and I have also great support from Nicolas Sedlmeier when talking about, when considering time-dependent phenomena. I had no time to present them today. So thank you so much for your attention. I would be happy to answer questions.